Hi students, now we are going to solve a problem based on speed of a transverse wave on a stretcher string. See the question carefully. And this question is taken from H.C. Verma. A circular loop of a string rotates about its axis on a frictionless horizontal plane at a uniform rate so that the tangential speed of any particle of the string is v. If a transverse disturbance is produced at a point of the loop, with what speed relative to the string will this disturbance travel on the string? This is now question given. You can try once if you want by pausing the video. Then you can see solution. Right, now see how we are starting that. First make diagram for that. Take one circle. This is now rotating with a tangential velocity that is v. So take it as v. Okay. Now a pulse is now produced on this. Then see that a pulse propagates now. That a pulse propagates now along the string length like this in circle. We have to find its velocity how much. We have to find its velocity how much with respect to string. Okay. Then see we have to focus first of all expression for speed of a transverse wave, that is root of t by mu. So first we should know what is tension. Okay, what is the tension in the string, right? Then see how to calculate. When it is rotating, suppose it is rotating like this, each and every element follows now circular path, right? When it rotates, we are taking now one small element. We are taking one small element on the string, right? Now this element is following circular path. Okay. Now we have to focus who is providing centripetal force. Again, this is same as the earlier question which we have discussed. That is tension by this part and tension by this part. Like this. Their components towards center. They provide now centripetal force, right? If angle is 2 theta, then we got tension in the previous question, that is 2t sine theta. This force is providing centripetal force. This force is providing centripetal force. Okay, right. Now the centripetal force equal to mass into acceleration. Then see what we get. It is 2t. Since angle is very small, in the place of a sine theta, taking as theta, that is equal to mass. Mass is now mu into and take here this angle, not theta. This is taken as 2 theta. Okay, right. So mu into r into 2 theta. This is arc length into mu gives mass m v square by r. Okay, then see what is now tension. So 2 theta gets cancelled, 2 theta gets cancelled, r gets cancelled. So T equal to mu v square. T equal to mu v square. Now substitute that in the relation v equal to root of t by mu. root of T by mu. Okay. Then see what we get. It is equal to mu gets cancelled. This V equal to V. Means speed of the transverse waves on the string with respect to string is equal to the tangential speed. Okay. So we have to focus on how to calculate tension. Once it is known, it is simply root of T by mu, right? So this calculation and earlier calculation almost the same, right? Okay. Now see next one. Energy in wave motion. So we are knowing that wave motion means it is a propagation of energy through oscillations, right? Let us take here. Let us take string shape is like this, and take shape is now, this is now shape of the string. Okay. This is X and this is Y. String is along X axis and the string vibrates along Y axis. Let us consider, let us consider one small element, okay, on the string. Now, since the string is vibrating, that element is having energy. I am repeating. When energy is propagating along the string length, each and every point on the string vibrates. Therefore, each and every point is having some energy. Now that energy we want to calculate. Okay. So we have taken now y equal to a sin omega t minus kx. Let us now calculate kinetic energy of a small element of length dx. It is kinetic energy of a small element of length dx. So kinetic energy equal to half m. M is now mu into dx. Length of the element dx. Mu is mass per unit length. So mu into dx gives mass of that element. Half m v square dou y by dou t gives velocity of the particle. So this is half m v square. So in the place of dou y by dou t, right? Take the value there. We got expression half mu dx into a square omega square cos square omega t minus kx. This is the kinetic energy of that small element. Okay, right. Now see carefully here one important point. That is, if you take this element, let us take its length was dx at mean position. Now its length equal to dl. That means because of tension, there is an extension in the string length. See carefully. Its original length equal to dx, but now present length equal to dl. Why these two are different means because of tension, its length has increased. Because of this elongation, it has elastic potential energy. Because of this elongation, it has elastic potential energy, and that we have to calculate. See how to calculate that. So potential energy of a small element of length dx is, it is equal to tension into extension in the element of length dx. See how we got this one. See extension, here tension is a constant. It is just like force into displacement. Now displacement is equal to elongation. That's why directly tension into elongation of that element. Okay. See how to get now that elongation. So I'm drawing diagram once again here. Its original length equal to dx. Present length is dy. Sorry, it is a dl. Let us take this as dy. Then we can write dl equal to, square root of this. Square root is for complete one. Square root of square of dx plus square of dy. Okay, and we are taking dx outside. It becomes square root of 1 plus dou y by dou x whole square. Okay, so we have taken now dx outside, 1 plus dou y by dou x whole square. Wait, here we have taken something wrong here. This minus 1 is not here. Okay, right. See once again, dx whole square plus dy whole square. Taking dx outside. Remaining is square root of 1 plus dou y by dou x whole square. Okay. Now, when dou y by dou x is very small, square of that is also very small. Then we can take approximation. I am writing that one. That is, it is just like 1 plus x whole power n. That is equal to 1 plus n into x. Here n equal to, n equal to 1 by 2. Okay. It is square root. Okay. Minus 1 not there. Then see what we get. Half. So actually here this calculation is now dx into this is what we have taken is, I think we have to correct this one. See what is this. I will write here once again, dx into 1 plus, it is 1 plus half into dou y by dou x whole square. Okay, that is now expression. So this is not correct. Okay, that is the next step, right? Now see the next step. Now we have to calculate what is elongation. Elongation is nothing but, I will write here, elongation is dl minus dx. Initial length minus present, final length minus initial length. Okay. Then we are going to get a half, okay, dx into dou y by dou x whole square. Okay, that is now elongation. Okay, now half into dou x into, sorry, dx into dou y by dou x whole square. That is elongation. Now tension into elongation. See next step. So tension into elongation. It is tension into elongation. Elongation we got half into dx into square of dou y by dou x. This is the potential energy. Now in the place of dou y by dou x, we are writing here a omega cos function and square of that. So finally we got half mu dx a square omega square cos square omega t minus kx. Right? This is potential energy of that small element whose length is dx. Right? And if you see equation 1 and equation 2, both are same, right? So equation 1, what we got? Half mu dx into A square omega square cos square omega t minus kx. That means that means kinetic and potential energies. Kinetic and potential energies of any small element are the same. So this is a very important conclusion. Potential energy and kinetic energy of any small element are same. Okay, that means if I am taking, for example, take here, suppose this is now shape of the string. Okay, if you take at point A, topmost point, velocity equal to 0 means kinetic energy equal to 0. Their potential energy also 0 because in this case, the kinetic and potential energies are same. So both are 0. So here many students having confusion here why they are same. Because earlier we have learned simple harmonic motion where potential energy maximum, their kinetic energy minimum, or kinetic energy maximum, potential energy is minimum. But in this case, both are same. Means both are minimum, both are maximum. So how this is possible? So having a confusion here, I'd explain that. Now see carefully. Suppose see we are taking one element, okay? One element on the string. If you observe, on this element work is done by the remaining part of the string. I am repeating. On this element work is done by remaining part of the string. That means its energy is not constant. Is a point clear? Or I will write here one more relation which we learned earlier. Work done by external force equal to delta K plus delta U. Now here on this element by external force, that tension by the remaining part of the string becomes external force. And by that external force work is done. That's why sum of a kinetic and potential is not a constant. Okay. So in case of a spring block system in SHM, we have taken that spring potential energy converts into kinetic or kinetic energy converts into spring potential energy because there on the system no work is done by external forces. That's why for that system total mechanical energy is a constant. But coming to here, we have taken one small element and on that element by remaining part of the string work is done. That's why kinetic energy plus potential energy of that small element is not a constant. Okay. So at extreme position, both are 0. And if you observe, if you take at mean position, slope is maximum, or I can say modulus of a slope. Okay. See carefully, potential energy dou y by dou x whole square. Dou y by dou x is slope, square of the slope, right? When slope is a maximum, potential energy is maximum. So at mean position, slope is maximum, right? So at mean position, potential energy of that element is maximum. That means kinetic energy is also maximum because both are same. We got same expression for both kinetic and potential. Therefore, at extreme positions, both kinetic and potential energy 0. At mean position, both are maximum. Okay. So this is very important point. That is what we have written here. The extreme positions, both are 0. At a mean position, both are maximum. Right? Okay. Now, total energy of any element of length dx. It is simply sum of potential and kinetic. Then we get now this one. Total energy for that element. Okay. And if you want to take average value for this one in one cycle, we know that for cos square function, average value in one cycle is a half. Therefore, therefore, average energy of any element, average energy of any element of length dx is half mu dx a square omega square. See, you can remember this like this. In simple harmonic motion, we have learned oscillation energy equal to half m omega square a square, right? So in the place of m, mu into dx, right? In case of SHM, we have learned that oscillation energy is half m omega square a square or half k a square, where k equal to m omega square, right? So it is very easy to remember also. Just half m v square in the place of mass mu into dx. Now let us calculate average power. So average power means it is a rate at which energy flows taking the average value. That means differentiate now this value. So when we differentiate this in the place of dx by dt, when we take derivative, dx by dt becomes now velocity of wave. So half mu omega square a square dx by dt, that is velocity of wave. Okay. And if you differentiate this, sorry, if you divide this cross section area of the spring, I'm repeating, if we divide power with the cross section area of the string, that gives average intensity. See here what happens is when you take mu value, mu by a, mu by a gives, sorry, better you can take in the place of figures to avoid confusion between amplitude and cross section area. So mu by s, that is equal to rho. So mu means mass per unit length. Dividing that with cross section area, that gives mass per unit volume. So we have taken here, it is half mu by a, sorry, mu by s, that is rho, right? Half rho omega square a square v. This is expression for average intensity. Okay. This is regarding energy in wave motion, right?